Deep learning has thrived on the backbone of residual connections, allowing gradients to flow through hundreds of layers. But as we push towards trillion-parameter models, standard architectures face a bottleneck. Today, we deconstruct mHC, Manifold-Constrained Hyper-Connections, DeepSeek's architectural breakthrough that redefines how information propagates in massive foundational models. The core idea extends the concept of hyperconnections. Standard residuals have a fixed width c. mHC expands this into a latent residual stream of width n times c. Imagine splitting a single-lane road into a massive multi-lane highway. This drastically increases the network's topological complexity and capacity, allowing for richer feature mixing without a proportional increase in flops. However, this expansion comes at a cost. In a standard hyperconnection, the mixing matrices are unconstrained. As signals propagate through depth L, the composite mapping deviates from the identity. We observe a signal explosion. Feature norms grow exponentially, leading to gradient collapse. The network becomes numerically unstable, making large-scale training impossible without severe hacks. DeepSeek's solution is geometric. Instead of allowing the residual mapping to wander anywhere in the vector space, we project it onto a specific Riemannian manifold. We constrain the linear mappings to exist strictly within a controlled geometric subspace. This ensures that no matter how deep the network gets, the signal transformation remains bounded and well-behaved. Specifically, we project the matrices onto the Birkhoff Polytope. This is the set of all doubly stochastic matrices. In this state, every row sums to 1, and every column sums to 1. Mathematically, this preserves the first moment, mean, of the features and strictly bounds the spectral norm of the transformation to less than or equal to 1, guaranteeing non-expansive signal propagation. To enforce this constraint in a differentiable way during backpropagation, we utilize the Sinkhorn-Knopp algorithm. We take the raw, chaotic learnable weights and apply an iterative normalization, first normalizing rows, then columns repeatedly. This converges rapidly, transforming the weights into a probability mass function that acts as a stable, soft routing mechanism. Theoretical stability is useless if it's too slow. Expanding the residual width n times hits the memory wall. In modern GPUs, arithmetic density, flops, has outpaced memory bandwidth. Writing these massive expanded tensors to high-bandwidth memory creates a severe I/O bottleneck, starving the tensor cores and reducing training throughput. To solve this, mHC implements low-level kernel optimizations. We use kernel fusion to keep intermediate expanded states in fast SRAM, L2 cache, avoiding round trips to HBM. Furthermore, a modified dual-pipe schedule splits computation and communication streams, perfectly overlapping the expensive all-to-all communication of Mo with the mHC tensor recomputation. The results are definitive. mHC achieves superior stability compared to standard hyperconnections and scales flawlessly to over 27 billion parameters. It offers a 13.3% throughput gain over unoptimized baselines with only a 6.7% overhead. By constraining topology to a stable manifold, DeepSeek has laid the groundwork for the next generation of efficient, ultra-deep architectures.